This is a 5-part series about measurement conditions for the focusing and parallel beam methods. The topics to be explained in Chapter 1 to 4 for the focusing method are X-ray tube selection, monochromatization of X-rays and background reduction, auto-alignment and preparation of samples, and the conditions of the standard measurement program. Chapter 5 includes the topics together from the X-ray tube selection to the conditions of the standard measurement program for the parallel beam method. Measurement conditions are very important factors to get high-quality data, which in turn leads to precise and accurate results of analyses. Even though an instrument has been correctly aligned, if a sample is measured under improper measurement conditions, the data quality will be very low, which leads to inaccurate analysis results. Therefore, you have to employ appropriate measurement conditions for a sample depending on the purpose to get high-quality data and the precise analysis results. Before starting the main topics, let me define high-quality data and introduce the X-ray diffractometer for the explanation in this series. There are 3 factors to consider for high-quality data: high peak intensity, high angle resolution, and high PB ratio. The PB ratio denotes the intensity ratio between a peak and background. When you get the data including 3 factors, namely the high-quality data, you must get the high precise and accurate results. Conversely, the low-quality data gives inaccurate results. Please keep in mind, programs of any application software will show a result without any indication about quality of the result. We have to realize that the reliability of the result depends on the measured data quality. I'll explain how to get high-quality data from this series of measurement conditions. First, I'll show the high peak intensity data from among the 3 factors. The high peak intensity data give the accurate peak angle, intensity, and width. In the case of low peak intensity data, there is a possibility to not observe small peaks from small amounts of substances in a sample. And also low peak intensity data suffers from large statistical fluctuations and leads to inaccurate information. The statistical fluctuations will be explained later in Chapter 4. The next factor is angular resolution. These 2 data are the same 5 overlapping peaks of silicon dioxide. The high angle resolution data on the left shows narrow peak widths and clear peak separation, whereas the right side data shows unclear peak separation due to the wide peak widths, that is considered to be low angle resolution data. Like this, the angular resolution is characterized the full width of half max of the peak. We can't get the accurate information from the low angle resolution data. The last factor is the PB ratio. The intensity ratio of a peak to background is called the PB ratio in the X-ray powder diffraction. A high PB ratio data shows high peak and low background intensities. Small peaks of a minor substance in a sample cannot be observed in a low PB ratio data, because they may be buried in the background. And next, let me introduce the primary diffractometers we've provided as Rigaku products. This table simply shows the differences in each diffractometer. The goniometer radius differs depending on the diffractometer: 150, 185, 285 and 300 millimeters. As the goniometer radius increases, the angular resolution increases. The diffractometers which have a multi-layer mirror can provide both the focusing and parallel beam methods by easy switching, and ones that don't have a multi-layer mirror are used mainly for the focusing method. The diffractometer for the explanation of the series such as the Ultima 3, Ultima 4 or TTR3 of theta type X-ray diffractometer has the goniometer radius of 285 mm. Now, I start to explain the measurement conditions of the focusing method and the parallel beam method about the theta goniometer with a 285 mm goniometer radius. This is the flow chart of the focusing method. When you measure a sample, there must first be a clear purpose such as qualitative analysis, residual stress, lattice constants refinement or other applications. And next, you should consider what kind of X-ray tube is suitable for that purpose. In practices, we use a copper X-ray tube for almost all measurements, because recently we can commonly use a monochromator. But occasionally we must select the kind of X-ray tube for the measurement with the K-beta filter method or the special purpose. I'll introduce a few kinds of X-ray tubes and the key points to consider for the X-ray tube selection. Next step is how to monochromate X-rays and reduce the background. I'll explain two methods of X-ray monochromatization, the K-beta filter and the monochromator methods. And as background reduction, I'll explain the pulse height analyzer, PHA, which functions to eliminate mainly white X-rays that contribute to the background. And then you execute the auto alignment including two theta, the pulse height analyzer, the profile measurement, and the counting loss measurement. I'll give the very simple explanation about the auto alignment and its result. Then I'll introduce how to prepare different kinds of samples. After that, you should set the conditions of the standard measurement program. I'll explain in some detail the scan axis, the method, the counting unit, the start and stop angles, the sampling width or step width, the scan speed or count time, the tube voltage and current, and the slit conditions. After setting the measurement conditions, you can measure the sample. Finally, you can use the measured data for the analysis. Now I start to explain the topic of Chapter 1, the X-ray tube selection from in the next slide. I show some X-ray tubes used for X-ray powder diffraction from long wavelength, chromium, to short wavelength, tungsten, in that order in the table. In the same sequence, the energy of the X-rays, it ranges from low to high. A chromium X-ray tube is mainly used for the residual stress measurement of iron-based samples. A manganese X-ray tube is used for the residual stress measurement of gamma iron, also called austenite, and others. An iron X-ray tube is used for the iron-based samples in the measurement with the K-beta filter method, or for ceramic samples of residual stress analysis. A cobalt X-ray tube is also used for the iron-based samples, and you can get the data of high peak intensity and PB ratio if you can use a monochromator. The next copper is the most common X-ray tube, and used for the standard measurements such as profile measurement, qualitative analysis and other applications. A molybdenum X-ray tube is used for the transmission measurement due to the short wavelength with high energy, and also used for the retained austenite measurement because it can give the peak positions at lower angles. A tungsten X-ray tube, which provides the shortest wavelength, is also used for the transmission measurement because of its high energy. This is a 4-part series about qualitative analysis of X-ray powder diffraction. I'll explain principles and features in Chapter 1. And I'll introduce databases used to identify composition of a sample in Chapter 2. Qualitative analysis of X-ray powder diffraction is also called identification. Recently, the mechanism of qualitative analysis is hard to comprehend for new users, due to computer programs we can use for identification without enough knowledge about qualitative analysis. I would like to present the Hannah-Walt method, although it is not used, in Chapter 3, which is a representative way of manual identification, and can be a good reference to understand qualitative analysis. The general outline of qualitative analysis of both the Hannah-Walt method and computer programs are the same, though details such as algorithms, procedures and others are not the same. Lastly, I'll explain some problems to be considered for identification in Chapter 4. What is qualitative analysis of X-ray powder diffraction? The answer is to reveal chemical components included in a sample. We can determine what substances are included in a sample as not only chemical elements, but also chemical compounds. This is one of the strong advantages of qualitative analysis. A given substance produces its own characteristic X-ray powder diffraction pattern. The chemical compound TiO2 has this pattern, and KCl shows this pattern. When both substances, TiO2 and KCl, are mixed together, both patterns are just superimposed like blue and red. Therefore, if each pattern can be correctly separated, we can determine that each substance, TiO2 and KCl, is included in the sample. The way of determining the presence of a substance in a sample is by comparing a pattern of an unknown sample, for instance, with that of a PDF card data in the ICDD database. Any X-ray diffraction pattern is characterized by a set of lattice spacing d values, which are calculated from diffraction peak angles depending on the wavelength of a target metal, and a set of relative intensity of peaks, I over I naught. We can identify a substance by comparison and verification of lattice spacing d values and relative intensities between an unknown and a PDF card. And when the d values and relative intensities of the unknown substance match very well to the substance of the PDF card in the database, the former is identical to the latter. The determination of substances by pattern comparison and verification is called identification. Here is a pattern of an unknown sample, and it's compared with patterns from PDF card data in the database, for example, substance A or substance B. It is clear that the pattern of the unknown sample is not identical to that of substance A, but identical to the pattern of substance B. After detailed comparison and verification, the unknown sample is determined to be identical to the known substance B in the database, which is an example of identification. Next, I'll introduce advantages and disadvantages as features of qualitative analysis of X-ray powder diffraction. There are two main advantages: composition analysis and state analysis. Composition analysis is a strong advantage. We can determine components of a sample not only by elements but also by chemical compounds. Moreover, we can find whether the substances are simply mixed or solid solution. And also we can distinguish the forms of the crystal polymorphism of compounds, or the forms of allotropic modification of elements through state analysis. Unfortunately, there are also two main disadvantages. The sample for qualitative analysis must be crystalline. Any sample of gas, amorphous solid or liquid cannot be identified. and also a substance which is unregistered in the database cannot be identified. Now I'll start to explain the main advantages. We can determine substances in a sample as chemical compounds, not only elements. For example, if a sample contains a compound AXBY, where A and B are elements, X and Y are stoichiometric coefficients such as Fe2O3. The ordinary composition analysis including fluorescent X-ray analysis shows only the presence of elements, A and B, namely iron and oxygen. On the other hand, qualitative analysis of the X-ray powder diffraction discloses the presence of the compound, Fe2O3. Furthermore, if a sample consists of 3 chemical compounds with elements only A and B, but different stoichiometric coefficients, for instance, AXBY, A2XB3Y, and A3XB4Y, every chemical compound would be disclosed by distinguishing each X-ray diffraction pattern. But fluorescent X-ray analysis would always indicate only the presence of elements A and B, in this case, iron and oxygen. When we measure the sample of the previous slide, we can see 3 patterns of chemical compounds: FeO, Fe2O3, and Fe3O4 superimposed in the data. And then we can identify each substance by comparing both patterns of the sample and the PDF card using computer programs. The second advantage is to distinguish each form of crystal polymorphism of chemical compounds and each form of allotropism of elements through state analysis. At first, I'll explain polymorphism, which is the ability of a solid material to exist in more than one form of crystal structure. Titanium dioxide, TiO2, has some polymorphisms such as rutile and anatase, among others. Both rutile and anatase have the same crystal system, tetragonal, but different crystal structures such as lattice parameters, space groups, and atomic coordinates, etc. And the information contributes to produce their characteristic X-ray diffraction patterns. Therefore, rutile and anatase in a sample are identified by distinguishing each pattern by X-ray diffraction analysis. But we can find only elements titanium and oxygen by fluorescent X-ray analysis. In spite of the superimposed patterns of the mixture with rutile and anatase, each pattern is separated and compared to PDF cards for identification.